When economists are analyzing the effects of changes in interest rates, they have to take into account a multitude of factors, often combining the equations and then using the derivative to find optimal solutions. Hi, my name is Jason Rosenberry, and in today's lesson we will be learning the rules of differentiation. Let's dive right in. Let's start with some rules. Rule 1. Derivative of a constant function. If f is the function with constant value c, then the derivative of f with respect to x is 0. In other words, the derivative of a constant is 0. Rule 2. Power rule for positive integer powers of x. If n is a positive integer, then the derivative of x to the n is n times x to the n minus 1. Here are two more rules. Rule 3. The constant multiple rule. If u is a differentiable function of x and c is a constant, then the derivative of cu with respect to x is equal to c times the derivative of u with respect to x. The sum and difference rule. If u and v are differentiable functions of x, their sum and difference are differentiable at every point where u and v are differentiable. At such points, the derivative of u plus or minus v with respect to x is equal to the derivative of u with respect to x plus or minus the derivative of v with respect to x. Now we should try some examples. For the following two functions, let's find dy dx. First one is y equals 2x plus 1. The second one is y equals x cubed over 3 plus x squared over 2 plus x. Let's look at the first one. We have y equals 2x plus 1. Using our shortcut rules for derivatives, y prime can be found by taking the derivative of each term. The derivative of 2x is 2, and the derivative of positive 1, being a constant, is 0. So if y is equal to 2x plus 1, y prime is equal to 2. Let's look at the second problem. I'm going to first rewrite this problem in a different form. Y equals x cubed over 3 is the same as 1/3 x cubed plus x squared over 2 is the same as 1/2 x squared plus our x. So we're going to use a couple of our rules. We're going to use the sum rule again, simply meaning we'll take the derivative of each term. We'll also be using the power rule and the constant multiple rule. So here we go with the derivative of the first term. So y prime would equal 3 times, we're going to take 3 times 1/3, which is 1, times x to the 3 minus 1, or x squared. Second term, we'll take 2 times 1/2, get 1. 1 times x is x, and again we decrease the exponent by 1, so that would just be x to the first power, and plus x, the derivative of x is 1. So y prime would equal x squared plus x plus 1. Let's try another example that uses these rules, as well as what a derivative means. Find the points on the curve below where the tangent is parallel to the x-axis. We're given y equals 2x cubed minus 3x squared minus 12x plus 20. So again, we want to find the points on this curve where the tangent lines at those points end up being parallel to the x-axis. So here's our function. We're going to first find the derivative. So y prime would equal 6x squared minus 6x minus 12. And being parallel to the x-axis implies that your tangent lines are horizontal, meaning the slopes are 0. So we're going to go ahead and set this derivative equal to 0. So 0 equals 6x squared minus 6x minus 12. We see that we can divide both sides by 6, giving us 0 equals x squared minus x minus 2. And again, we can solve this by factoring. X squared minus x minus 2 can be factored as x times x and we need a minus 2 and a plus 1, giving us two values of x. X is equal to negative 1 and also positive 2. So there we have found the two x coordinates of the 2 points where we would have horizontal tangent lines. So now we must find the y values. So we'll plug these values, negative 1 and also 2, back into the original equation to get their corresponding y values. So our 2 points would be negative 1, 27, and also 2, 0. Those are the locations where we would have tangent lines parallel to the x-axis. Let's move on to a rule for differentiating a product of functions. The product rule. The product of two differentiable functions u and v is differentiable, and the derivative of u times v with respect to x is u times the derivative of v with respect to x plus v times the derivative of u with respect to x. Let's try this out. Find dy dx. A, by applying the product rule, and then by B, by multiplying the factors first and then differentiating. So here's our function y equals the quantity x plus 1 times the quantity x squared plus 1. First we'll use the product rule. So we'll think of this as being u, and we'll think of this as being v. So y prime would be u x plus 1 times the derivative of v, which is 2x, plus v x squared plus 1 times the derivative of u, which is just 1. So multiplying this out, we would get y prime is equal to 2x squared plus 2x plus x squared plus 1. And then combining like terms, y prime looks like we get 3x squared plus 2x plus 1. So using the product rule, we get our derivative to be 3x squared plus 2x plus 1. Now that is not the only way that we could get our derivative. Part B wants us to go ahead and multiply this out and then differentiate. So let's multiply this out. Y equals x times x squared, x times 1, x squared times 1, and then a 1 times 1. So there I actually multiplied this out. So here we've rewritten y as a collection of terms. Now let's find y prime by differentiating each term. First term would be 3x squared plus 1 plus 2x, and the plus 1 at the end is a constant. That derivative would be 0. So again, rewriting these terms in descending order, we get 3x squared plus 2x plus 1, which was the same answer that we got using the product rule. Let's move on to the quotient rule. The quotient rule, at a point where v does not equal 0, the quotient y equals u over v of two differentiable functions is differentiable and is found by the following. The derivative of u over v with respect to x is equal to v times the derivative of u with respect to x minus u times derivative of v with respect to x, all over v squared. Let's try this out. Find dy dx for y equals x squared over 1 minus x cubed. So let's call the numerator u, and let's call the denominator v. Let's find y prime. Y prime is equal to v, 1 minus x cubed, times derivative of u, 2x, minus u, x squared, times derivative of v, which is negative 3x squared, all over v squared, or denominator squared, which is 1 minus x cubed, that quantity squared. Let's clean up the numerator. Y prime would equal 2x minus 2x to the fourth and it looks like we'll end up with a positive 3x to the fourth all over denominator squared, 1 minus x cubed, the quantity squared. We'll collect some like terms. 3x to the fourth minus 2x to the fourth is 1x to the fourth, and we have a plus 2x all over the quantity 1 minus x cubed squared. Let's use the quotient rule as well as the concept of derivative to work another example. Find the tangents to Newton's serpentine, which is given by y equals 4x over x squared plus 1 at the origin 0, 0 and at the point 1, 2. So again, we're trying to find the equations of the tangent lines to this graph at the point 0, 0 and at the point 1, 2. So we need to first start by finding the derivative. So if y is equal to 4x over x squared plus 1, so y prime would equal denominator x squared plus 1 times derivative of the numerator, which is just 4, minus the numerator 4x times the derivative of the denominator, which would be 2x all over the denominator squared, or x squared plus 1, the quantity squared. That gives us y prime is equal to, distributing the 4, we would get 4x squared plus 4 minus 8x squared all over the quantity x squared plus 1 squared, and combining like terms in the numerator gives us negative 4x squared plus 4 all over x squared plus 1, that quantity squared. Now let's use our derivative to find the slopes of the tangent lines. We have an expression for y prime, so now we'll find the slope of the tangent line at the point 0, 0 by substituting 0 in for x in the derivative. So for 0, 0, y prime gives us a value of positive 4, and evaluating y prime at the point 1, 2, meaning we'll let x equal 1, plugging x equals 1 into our derivative gives us a slope of 0. Now we can come up with the two equations of the lines. With our first situation at the point 0, 0, we get the equation of the line y equals 4x, and for the second one, since we have a slope of 0 that implies a horizontal line, then the equation of that line would be y equals 2. Let's look at another rule. Power rule for negative integer powers of x. If n is a negative integer and x does not equal 0, then the derivative of x to the n power with respect to x is n times x to the n minus 1. Let's try an example. Find an equation for the line tangent to the curve y equals x squared plus 3 over 2x at the point 1, 2. Support your answer graphically. Let's start by finding y prime using the power rule for negative exponents. So we're going to rewrite our problem, y equals x squared plus 3 over 2x. We can write this problem as y equals x squared over 2x plus 3 over 2x. And then that is equal to x over 2 plus 3 over 2, and we have an x in the denominator, which means we could write that as x to the negative 1. So we have y equals x over 2 plus 3/2 x to the negative 1. So now to find the derivative of y prime, taking the derivative of each term, the derivative of x over 2, or 1/2 x, is just 1/2. Now we take the derivative of this term using our new rule, so we'll take negative 1 times 3/2, which is negative 3/2, times x, and now we decrease the exponent by 1, so negative 1 minus 1 is negative 2. This means we can convert now back to a common denominator and write this derivative using one fraction. So we would have y prime equal to 1/2 minus 3 over, now getting rid of the negative exponent, we would have 2x squared in the denominator. And now combining our terms together using a common denominator, we would have the common denominator of 2x squared, giving us x squared minus 3 in the numerator. So y prime would equal x squared minus 3 all over 2x squared. So now let's evaluate our derivative y prime at the point 1, 2. So substituting 1 in for x into our derivative gives us a slope of -1. The y-intercept is 3. So the equation of our line would be y equals -x plus 3. Let's take a look at the graph to make sure this supports our answer. We're going to graph both the original function, and we're going to graph the equation of what we think is the tangent line, and we're hoping that that line is tangent to this curve at the point 1, 2. And as you can see here we are at the point 1, 2, and as you can see, that equation of that line gives us the graph of the tangent line to that curve at 1, 2. Let's move on to higher order derivatives. We will discuss these by means of an example. Find the first 4 derivatives of y equals x cubed minus 5x squared plus 2. Let's find the first derivative, y prime. Again, using differentiation rules, we'll differentiate each term, giving us 3x squared minus 10x. Now we have what's known as the second derivative, or the derivative of the first derivative. So y double prime. Again, differentiating each term. Differentiate 3x squared is 6x. Differentiate minus 10x. That's a minus 10. Now we'll differentiate the third derivative, y triple prime. Derivative of each term again. Derivative of 6x is 6. Derivative of -10 is 0. And then we have the fourth derivative, which we write y with a 4 in parentheses. The fourth derivative is the derivative of 6, and that's just 0. Now it's time for you to try a problem. Find the first 4 derivatives of y equals x to the 4th plus x cubed minus 2x squared plus x minus 5. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So our first derivative, y prime, will be 4x cubed plus 3x squared minus 4x plus 1. The second derivative would equal 12x squared plus 6x minus 4. Third derivative is 24x plus 6. And the fourth derivative, which can be used, you can use 4 symbols, and also the other notation is used in the parentheses, the number 4, and that derivative would be 24. In this lesson we explored rules of differentiation and higher order derivatives. Be sure to work the exercises that your teacher assigns. We'll see you next time.